General element notation. Hello everyone. To begin, let's recall what we have already covered. In our previous sections, we established that a matrix is essentially a rectangular array of numbers, organized into rows and columns. Now, while this is simple for small matrices, imagine working with a matrix that has dozens of rows and columns. In such cases, it becomes quite impractical to refer to a specific number just by pointing to it or describing its location vaguely. To solve this problem, mathematicians have developed a standardized addressing system known as general element notation. You can think of this as a way to give every single number within the matrix its own unique address. This system allows us to identify the exact position of any element within a matrix using a pair of indices. Over the next few slides, we will explore exactly how these indices work and how to use them to navigate any matrix, regardless of its size. Understanding the notation $. Now that we have established the need for a standardized addressing system, let's look at how we actually write it. To identify a specific element within a matrix, we use a lowercase letter, which is typically the same letter used for the matrix itself, accompanied by two subscripts. For instance, if the matrix is named capital A, a general element within that matrix is denoted as lowercase a sub ij. You can think of these subscripts I and j as coordinates. The first subscript, I, represents the row number, while the second subscript, j, represents the column number. Therefore, the notation lowercase a sub I, j refers specifically to the element located in the ith row and the jth column. In the next slide, we will look at some concrete examples to see this in action. Example for clarity. First, consider a sub 1-1. Following the rule we just discussed, the first index represents the row and the second represents the column. Therefore, a sub 1-1 refers to the element located in the first row and the first column. Next, let us look at a sub 2-3. Here, the first subscript is 2 and the second is 3. This means we move to the second row and then across to the third column. Thus, a sub 2-3 is the element in the second row and third column. Finally, let us examine a sub 3-2. It is important to pay close attention here so we do not confuse this with the previous example. In this case, the first index is 3 and the second is 2, meaning this element is located in the third row and the second column. Now that we have established the theory behind the subscripts, let us look at a few concrete examples to see how this addressing system works in practice. Once you are comfortable with how to identify these specific elements, we can move forward to discuss how to represent an entire matrix using this general notation. The general representation of a matrix. Now that we have seen how to identify individual elements using specific indices, let's move on to how we describe an entire matrix in a general way. In many cases, especially when dealing with very large datasets, it is impractical to list every single number within a matrix. To handle this, mathematicians use a general mathematical form to represent the matrix as a whole. For example, if we have a matrix, which we will call capital A, consisting of m rows and n columns, we represent it as capital A equals bracket a sub ij with a subscript of m by n. However, to make this definition mathematically rigorous and precise, we must add a few essential conditions. We specify that 1 is less than or equal to I, which is less than or equal to m, and similarly, 1 is less than or equal to j, which is less than or equal to n. Furthermore, we state that both I and j must belong to the set of natural numbers. I know this looks like a lot of symbols at once, so in the next slide, we will break down each part of this notation to understand exactly what it tells us. Breaking down this notation. First, the notation a sub ij enclosed in square brackets indicates that the matrix is composed of these individual elements, where I and j serve as the coordinates we discussed in the previous slides. Next, the m cross n specifies the order of the matrix. As a reminder, this always tells us the total number of rows first, followed by the total number of columns. Then we have the condition. 1 is less than or equal to I, which is less than or equal to m. This simply means that our row index, I, must start at 1 and can go up to the maximum number of rows, m. Similarly, the expression 1 is less than or equal to j, which is less than or equal to n, tells us that the column index, j, starts at 1 and continues up to the total number of columns, n. Finally, the statement that I and j belong to the set of natural numbers is a critical detail. This indicates that the indices must be positive integers, as it is logically impossible to have a 0th row or a half column in a matrix. Now that we have seen the general representation of a matrix, let us break down exactly what each part of that mathematical expression means to ensure there is no confusion. Understanding these formal constraints is essential because it allows us to translate real-world data into a matrix format, which is exactly what we will do in the next section. Real-world application, inventory management. Now that we have covered the theoretical side of general element notation, let us apply these concepts to a real-world scenario to see how they are actually used in practice. Imagine a store that sells 2 types of electronics, specifically laptops and tablets, across 3 different branches, which we will call Branch A, Branch B, and Branch C. To keep track of the stock levels efficiently, the manager decides to organize this data into a matrix, which we will denote as Matrix S. The first step in this process is to organize the raw data into a structured table. In this case, we will assign the products to the rows. Since we have laptops and tablets, the total number of rows, represented by the variable m, equals 2. Similarly, we will assign the branches to the columns. Since there are 3 branches, the total number of columns, represented by the variable n, equals 3. By defining these dimensions first, we can now move forward to construct the actual matrix in the next slide. Representing data as a matrix. Now that we have organized our data into a table in the previous step, let's move to step 2, where we represent this information as a matrix, which we will call Matrix S. Looking at the screen, Matrix S is presented as a rectangular array of numbers. The first row consists of the values 15, 20, and 12, which correspond to the laptop stock across the 3 branches. Directly below that, the second row contains the values 30, 25, and 40, representing the tablet stock for those same branches. Notice how the structure of this matrix perfectly mirrors the table we just discussed, maintaining 2 rows and 3 columns. By converting our data into this format, we are now ready to use the general element notation to pinpoint specific values, which we will explore in the next slide. Using element notation to find specific data. Now that we have organized our inventory data into Matrix S, let's move to step 3, where we actually use element notation to retrieve specific information. Suppose the manager wants to find the exact number of tablets available at Branch B. To do this, we apply the addressing system we discussed earlier. First, we identify the row. Since tablets are listed in the second row of our matrix, our row index, I, equals 2. Next, we identify the column. Since Branch B is the second column, our column index, j, also equals 2. By combining these 2 indices, we can see that the required element is denoted as S sub 2. Finally, by looking at the intersection of the second row and the second column in our matrix, we find that S sub 2 equals 25. This tells the manager that there are exactly 25 tablets at Branch B. Common mistakes to avoid. First, let's talk about reversing the indices. The most frequent mistake students make is swapping the row and column positions. To prevent this, I want you to memorize a simple phrase. Row then column, or just remember the initials RC, for example. If you encounter the notation a sub 1-2, it would be incorrect to assume it refers to the first column and second row. Instead, the correct interpretation is that it refers to the element located in the first row and the second column. Secondly, be mindful of where the counting begins. Some of you may be familiar with computer programming languages, such as Python, where indexing starts at 0. However, in the field of mathematics, and specifically within the NCERT curriculum, matrix indexing always starts at 1. You will never have a 0th row or a 0th column in these problems. Finally, please be careful not to confuse the matrix itself with its individual elements. This is a matter of notation. A capital letter, such as capital A, refers to the entire matrix as a whole. In contrast, the lowercase letter with subscripts, such as a sub ij, refers to a single specific number residing inside that matrix. Now that we have seen how to apply this notation to a real-world scenario, like inventory management, it is important to discuss some common pitfalls to ensure you don't make avoidable errors in your exams. Keep these 3 distinctions in mind as we move forward to our final summary of the key takeaways. Key takeaways. To wrap up our lesson on general element notation, let's go through the key takeaways to ensure everything is clear. First, regarding the element address. Remember that the notation, a sub ij, is essentially the address of a specific number within a matrix, where I identifies the row and j identifies the column. Second, let's review the general form. When you see capital A equals a sub ij in brackets with a subscript of m by n, this is the mathematical way of representing a matrix that consists of m rows and n columns. Third, keep in mind the index constraints. As we discussed when talking about common mistakes, the indices I and j must always be natural numbers starting from 1. This means you will never encounter a row 0 or a row 0.5 in this curriculum. Finally, always be mindful of the order of identification. To avoid swapping your coordinates, always identify the horizontal position, the row first, followed by the vertical position, the column. Just remember the RC rule, row then column.